The creation of the Osman Gazi Suspension Bridge, a monumental feat of engineering that stands as the crowning jewel of the Gebze or Benghazi-Izmir motorway, began with the meticulous construction of the caissons, massive concrete structures essential for anchoring the bridge's piers deep into the seabed of Izmit Bay. This ambitious endeavor required a blend of technical expertise, innovation, and unwavering determination. Engineers and workers embarked on a journey marked by challenges and triumphs, pushing the boundaries of possibility to realize a vision that would redefine Turkey's infrastructure landscape. The process of crafting the caissons was a meticulous affair, undertaken with precision and care to ensure the structural integrity of these colossal concrete giants. Specialized molds were constructed, each designed to shape the raw materials into the desired form with exacting accuracy. Layers of reinforced concrete were poured and allowed to cure, gradually giving rise to the sturdy foundations upon which the bridge would ultimately rest. As the caissons took shape in the sprawling construction yards, a sense of anticipation hung in the air, foreshadowing the monumental tasks that lay ahead. With the caissons nearing completion, attention turned to the intricate operation of sinking them into the depths of Izmit Bay, a process fraught with logistical challenges and technical complexities. Specialized vessels equipped with advanced lifting mechanisms were mobilized, their towering cranes poised to hoist the massive structures into position. Each caisson was carefully maneuvered into place, guided by a team of skilled operators who navigated the treacherous waters with precision and expertise. Against the backdrop of the bay's tranquil surface, the sight of these behemoths slowly descending into the abyss was a testament to human ingenuity and perseverance. As the caissons settled into their designated positions on the seabed, the next phase of the construction process unfolded with meticulous precision. Engineers and workers embarked on the arduous task of laying the foundation for the bridge's piers, a task that required meticulous planning and attention to detail. Using advanced drilling equipment and cutting-edge techniques, they bored deep into the seabed, creating stable footings upon which the towering structures would be anchored. With each passing day, the bridge began to take shape, its skeletal form rising majestically from the depths of the bay, a symbol of progress and innovation. Amidst the rhythmic hum of machinery and the bustle of activity, the construction of the bridge's main span commenced, marking a significant milestone in the realization of this ambitious undertaking. Mammoth steel cables, meticulously woven and tensioned, stretched across the expanse of the bay, forming the backbone of the suspension bridge. With meticulous precision, the main span was hoisted into position, a feat of engineering prowess that captured the imagination of onlookers around the world. As the main span soared gracefully across the bay, attention turned to the intricate task of assembling the roadway, the final piece of the puzzle in completing the Osman Gazi Suspension Bridge. Section by section, the roadway took shape, with workers meticulously laying each component to form a seamless thoroughfare that would connect distant shores and unite communities. Against the backdrop of the azure sky and the gentle lapping of the waves, the bridge emerged as a triumph of human endeavor, a testament to the power of collaboration and innovation. With the final section of road locked into place, the construction of the Osman Gazi Suspension Bridge reached its triumphant conclusion. Turkey's longest bridge, and a symbol of its aspirations for the future, it stood as a towering testament to the ingenuity and determination of its creators. With a main span stretching an impressive 1,550 meters, it ranked among the longest suspension bridges in the world, a testament to Turkey's emergence as a global leader in infrastructure development. As vehicles traversed its expanse, they did so with a sense of awe and wonder, marveling at the sheer scale and grandeur of this engineering marvel. The Osman Gazi Suspension Bridge was more than just a crossing. It was a symbol of progress and possibility, a gateway to new horizons, and a testament to the indomitable spirit of human innovation. The Osman Gazi Suspension Bridge stands as a marvel of modern engineering, a towering testament to human ingenuity and perseverance. Stretching majestically across the azure waters of the Sea of Marmara, it serves as the crown jewel of the Gebze-Orhan Gazi-Izmir Highway, linking the bustling metropolis of Istanbul with the vibrant city of Izmir. With a main span of 1,550 meters, it ranks as the fourth longest suspension bridge in the world and the longest in Turkey, a breathtaking symbol of the nation's commitment to advancing its infrastructure. Designed to withstand the forces of nature and the relentless passage of time, the bridge represents the pinnacle of technological achievement, blending seamlessly into the natural beauty of its surroundings, while simultaneously standing as a testament to human ambition. The Osman Gazi Suspension Bridge owes its impressive stature to a meticulous design process that prioritized both form and function. Engineers and architects collaborated closely to conceive a structure that would not only span the vast expanse of Izmit Bay, but also complement the region's scenic landscape. The result is a graceful, sweeping silhouette that seems to defy gravity, its sleek lines cutting through the air with an elegance that belies its immense size. From the soaring towers that anchor the suspension cables, to the intricate lattice of steel that forms the roadway, every element of the bridge's design serves a purpose, combining aesthetics with structural integrity in perfect harmony. Yet, behind the bridge's breathtaking facade lies a complex network of materials and mechanisms meticulously engineered to withstand the harshest of conditions. The main span, supported by a series of massive steel cables, acts as the backbone of the structure, distributing the weight of vehicles and passengers with remarkable efficiency. Each cable is carefully tensioned to ensure optimal stability, while the bridge's sleek profile minimizes wind resistance, allowing it to withstand even the fiercest of storms. Beneath the surface, massive concrete caissons anchor the bridge's piers deep into the seabed, providing a solid foundation capable of withstanding the forces of nature for generations to come. It is a triumph of modern engineering, a testament to the power of human ingenuity to overcome even the most daunting of challenges. The construction of the Osman Gazi Suspension Bridge was no small feat, requiring the combined efforts of thousands of skilled workers and engineers. The process began with the careful selection of materials, with each component of the bridge meticulously tested and evaluated to ensure its strength and durability. Massive concrete molds were constructed to shape the caissons, while state-of-the-art steel fabrication facilities churned out the intricate components that would form the bridge's superstructure. As the pieces of the puzzle began to come together, teams of construction workers labored tirelessly to assemble the bridge piece by piece, their efforts fueled by a shared sense of purpose and determination. One of the most challenging aspects of the bridge's construction was the installation of the submerged towers, massive structures that serve as the foundation for the suspension cables. Specialized vessels equipped with advanced lifting mechanisms were deployed to maneuver these behemoths into position, their towering cranes hoisting the towering pillars into place with remarkable precision. Against the backdrop of the bay's tranquil waters, the sight of the submerged towers rising from the depths was a testament to human ingenuity and perseverance, a tangible reminder of the extraordinary lengths to which humanity will go to conquer the forces of nature. As the construction of the Osman Gazi Suspension Bridge neared completion, anticipation grew among the public, eager to witness the unveiling of this engineering marvel. Finally, after years of tireless effort and unwavering dedication, the bridge was ready to be opened to the world, a gleaming symbol of progress and innovation. Today, as vehicles traverse its expanse, they do so with a sense of awe and wonder, marveling at the sheer scale and grandeur of this architectural masterpiece. The Osman Gazi Suspension Bridge is more than just a crossing. It is a testament to the indomitable spirit of human ambition, a beacon of hope and progress that will stand for generations to come. In November 2014, the SBB commissioned the Arge Marty Eppenberg with the main lot of the Eppenberg Tunnel. The basis for success was laid with the construction of efficient and high-performance infrastructure at the installation sites in Waschnau and Gretzenbach. In addition to the underground tunneling work, the employees of Arge Marty Eppenberg have been engaged in extensive special foundation and engineering concrete work in the portal areas. For over 2.5 years, Marty Technic provided the conveyor belt systems, and a mobile and modular gravel plant was supplied by Cimatec. The railway line between Olten and Aarau consists of 2 or 3 tracks, and serves as the bottleneck for the 4-track stretch between Bern and Zurich. Therefore, to accommodate 4 continuous tracks, additional space is needed, which is lacking in the built-up area of Schonenwerd. Hence, Marty is constructing a 2-lane bypass for the SBB in this area. The new route mainly traverses the approximately 3,100-meter-long Eggenberg Tunnel, with the majority of it, around 2,600 meters, being excavated underground using a tunnel boring machine, TBM, over 100 meters long. However, tunnel construction underground is only half the task. An equal amount of work involves the surface areas of the tunnel, particularly at the eastern portal, where a massive excavation pit was created on the slope of the Seltenberg. Here, the tunnel boring machine will later be assembled. Over a length of over 300 meters, various techniques were employed to secure the slope for tunnel construction. The heavily trafficked Cantonal Road had to be rerouted multiple times. The existing above-ground railway line includes the Schonenwerd station, which must continue to be accessible in both directions, while railway tracks in the same direction must always be adjacent in the rail network. For unobstructed entry into the tunnel, a passage has to be built beneath the tunnel tracks. The construction of shafts and crossing tunnels in a confined space between heavily trafficked roads, combined with the slope at Eppenberg, presents an impressive and extremely complex construction site. Most of the surface construction work takes place on the narrow strip between the temporary cantonal road and the railway line. For the excavation pit securing and the definitive structures, over 9 kilometers of board piles were drilled, in addition to approximately 24,000 square meters of prefabricated sheet pile walls, covering approximately 1/3 of a football field. Working with heavy equipment in close proximity to fast-moving trains and cars requires the highest concentration. In the area of the single-track tunnel, the construction elements rise up to 26 meters high. Upon completion of the excavation pit, the actual tunnel is built. The tunnel must later withstand the pressure of the steep slope and is extremely massive. Mobile formwork trolleys are used for the concrete works. During the tunnel construction, the mountain tunneling started from the front area of the excavation pit, initially passing through loose material unsuitable for the tunnel boring machine. Therefore, the first part of the tunnel is constructed using the pipe umbrella method, breaking the tunnel into 10-meter sections under the protection of the pre-installed umbrella shield. After about 60 meters of excavation, enough coverage with solid rock is achieved, completing the shield tunnel. Subsequently, the tunnel boring machine assembly can finally commence at the portal that had been reserved for the excavation works. In October 2016, the cutting head was lifted, and in January 2017, the machine began its journey through the mountain. As the machine advances, the cutting tools on the nearly 13-meter-wide cutting head under high pressure break through the rock, continuously removing debris through openings in the cutter head. The loosened material is collected by the machine's scoop and transported to a conveyor belt at the center of the machine through the rotation of the cutter head. When drilling in dry rock, the material behind the cutter head must be dusted. The TBM's drill head exerts pressure of up to 20,000 kilonewtons through 48 thrust cylinders, moving forward against a pressure ring at the already built Tower 2. After every 2 meters, the machine stops, and the pressure is relieved to insert a tunnel ring made up of 6 ring segments into the gap. These segments interlock with each other, with the upper segments temporarily secured by rolling cylinders to stiffen the tunnel. When the crown segment is positioned, the lateral segments are pushed upwards radially until the ring is closed. The closure stone is then installed in the gap, completing the ring. After about 20 minutes of ring construction, the machine resumes its advance. Injection channels in the machine's shield inject grout into the gap between the segments and the rock to solidify the tunnel in the rock. In the upper tunnel area, the gap between the segments is filled with gravel through openings in the segments. The excavated material is transported away by a conveyor belt suspended from the tunnel's vault, continuously extending the conveyor belt. At the other end of the belt, new belt is released continuously through a belt accumulator. Simultaneously, segments for the next ring are delivered to the machine. The segments are always manufactured on-site. The filled segments pass through a 55-degree warm air channel. For the 6 segments of a ring, there are also 6 forms in rotation. Different-sized twin rings are used for left and right curves of the tunnel. The tunnel's geological layers are traversed during its journey through the Eppenberg, encountering different geological strata. The layers of Eppenberg in the east can be partly processed and recycled. The lower freshwater mass in the middle tunnel area is unusable and must be transported away. The lower terrace gravel in the west, on the other hand, is highly suitable for use as a concrete aggregate. Therefore, Marty developed and built a new gravel plant specifically for the Eppenberg project, which is modular and can be relocated to a new construction site in a few weeks. In the plant, the excavated material is washed, processed into gravel, and finally sorted into different sizes for concrete production. Unsuitable material for concrete production is stored temporarily and later used for backfilling. The unusable muck is transported by truck to fill the rehabilitated hazardous waste landfill in Colican. Through extensive processing and reuse on site, Marty achieved a significant reduction in the number of truck trips required for the project. From the gravel plant's silo, the gravel is transported across the railway line to the concrete plant by conveyor belt. The railway line intersects the installation site and the road running through the construction site, posing significant challenges to construction logistics. Despite this, the participating Marty companies were able to develop efficient solutions and infrastructure through good cooperation. The tunnel has 2 emergency exits and 1 escape tunnel. The tunnel segments were constructed using precast concrete elements, while the shafts were conventionally excavated from above. The tunnel boring machine has now passed through 1,800 meters of tunnel in slightly over 5 months, traversing the Effingham layers and the mass. The upcoming Ida Terrace gravel is highly groundwater-bearing. To prevent water from entering the machine uncontrollably, it is converted to hydroshield tunneling. The conversion takes place within the protective wall of a specially constructed tower, where the machine has dug its own garage. In hydroshield tunneling, the front part of the machine is sealed and pressurized. This pressure counteracts the groundwater and soil pressure, with the cutters continuously excavating the material. The excavated material is transported to the surface through the inner shell of the machine, while a stable annular gap is created by the filling water and the bentonite suspension. The water pressure is increased as the machine advances, with the height of the grouting tubes in the gap also increasing accordingly. The machine has now reached the last 300 meters of the tunnel and is cutting through the partially weathered limestones of the fresh mass. As the tunnel progresses towards the west, the alignment becomes increasingly difficult due to the topography, with the tunnel cutting through a sharp curve and steep gradient. The tunnel boring machine successfully completed the excavation in November 2017. The breakthrough, which had been anticipated for weeks, finally occurred. With this, the main construction work on the Eppenberg tunnel was completed.